previous lecture, I explained when the practical transformer is operating under load conditions. Now, moving to the next concept, equivalent circuit resistance of a single phase transformer. Equivalent circuit resistance of a single phase transformer. What is our first assumption? The first assumption is permeability of transformer core is infinity. So we are already considered with a finite permeability. And the second one is core losses is not equal to 0. Coming to the practical one. And third, we are considering the resistance. The resistance of the winding is also not equal to 0. But in an ideal case, we are assuming that core losses is 0 and the resistance of the winding is 0. But if the transformer winding has resistances, how many windings the transformer has? How many windings? There are two windings. One is a primary winding and another one is secondary winding. Or see here, it is HV winding and LV winding. So the supply which is given to the winding is called the primary winding. So here we are considering the resistance. The primary winding resistance is R1. The secondary winding resistance is R2. And here I am connecting a load. The primary winding draws a current of I1. The EMFs which is induced in a windings is E1 and E2. E1 is the primary induced EMF, E2 is the secondary induced EMF. The current flowing through secondary winding is I2 and the load is also I2. And the terminal voltage is V2. So again the same story. If the current flows through windings, which will produce an alternating flux in the core. So the transformer symbolic representation is like this. So the primary winding resistance is R1 and these two lines are represents the, it is a iron core transformer. So these two lines are represents, it is a iron core transformer. So the current flows through primary is I1, the current flows through secondary is I2, primary induced EMF is E1, secondary induced EMF is E2, and V2 is the terminal voltage. And these two lines are represented as iron core transformer. So if the lines are not there, then this type of transformer is called air core transformer. Air core transformer. Copper loss in the primary winding. The primary winding current is I1. Generally the copper loss formula is I square R. So I1 square into R1. The copper loss in the secondary winding is I2 square into R2. Now the total copper loss is equal to I1 square R1 plus I2 square into R2. If the secondary winding resistance is shifted to primary side, what is the condition for shifting of resistance? Copper loss before transfer of resistance. copper loss before transfer of resistance should be equal to copper loss after transfer of resistance. See, the secondary winding resistance is shifted to primary side. Now that will becomes R2 dash. This is R1. This is the primary winding. The secondary winding is directly connected to load. The current flows through load is load current, that is the secondary current is I2, and this one is I1, primary current. So before transfer of resistance means what is the current flows through? R2 is I2. Then I2 square R2 is equal to, after shifting, the current which is flowing is I1 square into R2 dash. Finally, I can get this R2 dash is equal to I2 by I1 whole square into R2. So R2 divided by K square. Now you got it out. I2 by I1 is K R naught, 1 by K R naught. So we have one relationship, E2 by E1 is equal to N2 by N1 is equal to I2 dash by I2. What is the primary current? I1 is a phasor sum of I0 bar plus I2 dash bar. But by neglecting the no load current, we can write it as I1 divided by I2, that should be equal to K. So that's why I am writing as K is equal to I1 by I2, but here I2 by I1 can be written as 1 by K. Now what is the total resistance when referred to primary? R01 is equal to R1 plus R2 dash R1 plus R2 by K square. This is called total resistance when referred to primary. And R02 is equal to, similarly, this is called the total resistance when referred to secondary. So we should find out now. So the primary winding resistance is shifted to secondary side, that will becomes R1 dash. The secondary winding resistance is R2, is our load, and the current which is flowing through this is I2, and here it is I1. Before shifting, the current flowing through this one is I1 square into R1 dash is equal to I2 square into R2. The R1 dash is equal to I2 is I1 square into R1, I1 square into R1. We want to shift the primary winding resistance to secondary side. I1 square R1 to I2 square into R1 dash, I2 square into R1 dash. Then R1 dash is equal to I1 by I2 whole square into R1, that is K square times of R1. So this is called the R02, R subscript 02, that is total resistance when referred to secondary. When referred to secondary is equal to R2 plus R1 dash, R2 plus K square times of R1. See, if you apply KVL to this loop, see these are the polarities. If you apply KVL to this loop, minus V, neglecting the Lenz law, plus I1 R1 plus E1 is equal to 0. I am following the notation. When the current enters into the positive terminal, can be treated as positive. So current enters into the positive terminal can be treated as positive, means I1 R1 plus I1 R1 plus E1 minus V equal to 0, and I1 R1 is equal to V minus E1. I1 is equal to V minus E1 divided by R1. So most of the students, they have a doubt that in the previous lecture how I1 is equal to V minus E1 divided by R1. I think your doubt is clarified now. And this is the total resistance when referred to primary. R01 is equal to R1 plus R2 dash R1 plus R2 by K square, and total resistance when referred to secondary is R2 plus R1 dash, that should be equal to R2 plus K square R1. So in this lecture I will solve the most repeated problem on equivalent resistance when referred to primary and when referred to secondary. So a 40 kVA transformer with the ratio of 2000 volts divided by 250 volts. This is called the primary induced EMF, and this one is secondary induced EMF. Has a primary resistance of 1.15 ohms. See, R1 is equal to 1.15 ohms, and the secondary resistance is R2 is equal to 0.0155 ohms. Suppose in the problem he may confuse, if he gives 250 by 2000 volts, how can you choose the primary induced EMF as a 250 or 2000? See the winding resistance. If the winding resistance is more, that means the induced EMF in the primary winding is more. If the winding resistance is less, the induced EMF in the resistance side, that will be low. R1 is equal to 1.15, so that's why it is called as a E1 is at high voltage, E2 is at low voltage. E1 is the primary winding induced EMF, and this one is secondary winding induced EMF. Now I can write it as E1 is equal to 2000 volts, E2 is equal to 250 volts. And now what is the formula? Total resistance when referred to primary R01 is equal to R1 plus R2 dash R1 plus R2 by K square. What is K? K is equal to E2 divided by E1. So that is 250 divided by 2000. So 250 divided by 2000 is equal to 0.125. The R1 value is 1.15 plus R2 value is 0.0155 divided by K square, 0.125 whole square. Now what is the answer? Total resistance when referred to primary, that should be equal to 2.142 ohms. The total resistance when referred to secondary R02 is equal to R2 plus R1 dash, it is R2 plus K square times of R1. 1.15 is R1 volts into K square. K square is 0.125. So 0.125 whole square plus what is R2? R2 is equal to 0.0155. Students, don't confuse here. So this is K square R1. K square R1 plus this one is R2. Okay, 0.0155 plus 1.15 into 0.125 whole square, then I will get it as 0.03346 ohms. and after that he is asking the total resistance drop on full load. For that I2 into R02, that is the second bit. How can I calculate I2 value? See, in the given data is given as 40 kVA. So S is equal to 40 kVA. I2 is equal to kVA divided by E2. That means secondary induced EMF. Then I will get the current. Volt ampere divided by voltage. Then I get the ampere. That is called the current. So 40 into 10 to the power of 3 divided by secondary induced EMF is 250. 250 value 40 into 10 to the power of 3. I am calculating in Cal C. Divided by 250 is equal to 160 amperes. But he is asking I2 or R02. So that is a drop in secondary side resistance. The total secondary side resistance means total resistance when referred to R02. So 160 into R02 into 0.0346, that is 5.03346 is equal to 5.3536 volts. This is the drop in the total resistance drop on full load. Total resistance drop on full load when referred to secondary side. Suppose if you substitute I1 into R01 also, you will get the same answer, that is 5.35. The total copper loss. What is the total copper loss formula? You can use I1 square R01 or I2 square R02. So total copper loss on full load is equal to I2 is 160 whole square into the R02 value. What is the R02 value? 0.3346. So finally I got it as 856.576 watts. So this is the most important problem, and this is a previous year problem in one of the university.